I'm Petar Povovsky, and this is my perspective on the challenges in beyond 5G and 6G systems. So, this talk, I'm going to focus on three different segments. One is the further research, which goes along the line of the research we have been doing in the past years. And this is covering two topics. One is spectrum for heterogeneous connectivity, and the other is data-driven performance guarantees and the use of machine learning in optimization of communication systems. Another one is related to the new constraints, which are the requirements from the citizens and providing reassurance and guarantees for health effects of the wireless systems, which is a big topic these days. And also new opportunities and applications for communication systems, such as true remote presence, which we see it as a very important application these days when most of us are working from home. Then new communication media and modes, such as quantum communications and metamaterials. Then another development are the data markets and the integration of distributed ledgers with communication system and especially with the Internet of Things systems. Let's first look into spectrum issues. And here is a relation between 5G and spectrum questions. So 5G brings a number of different innovations, but in my opinion, perhaps the main innovation in 5G is that it tries to offer a platform that is going to flexibly support heterogeneous services or services with heterogeneous requirements. So we all know that the cornerstones of 5G are the three types of services, eMBB, massive machine type communication, and ultra reliable low latency communication. So basically 5G sees these three generic services as something that can be created on top of a flexible platform of the 5G air interface. So on the other hand, 5G was created under certain assumption about the spectrum usage and spectrum licensing. But once 5G started to get standardized and once we started to understand better what are the applications and especially the services in vertical industries, there started to emerge new spectrum usage modes. And here I'm primarily thinking about private networks for industrial connectivity and local licensing. So if we look into what the European Commission is thinking, what we have learned from the platform approach in 5G is that we can think of the concept of slicing. And slicing of the spectrum means that the spectrum, the same spectrum can support heterogeneous services or services with heterogeneous requirements, except for the shared nature of the wireless medium and the wireless spectrum does not make it obvious how to divide the resources of the spectrum to different users. So basically the slicing can be non-orthogonal. So basically what this heterogeneous connectivity is bringing to the table for spectrum are the new modes and schemes that enable to trade off requirements between different services. For example, this figure here says that if there are two users, one of which is wants critical connectivity and the other one wants broadband rate, we would like to, if they share the same spectrum, we would like them to trade off the level of activity of the critical user versus the rate of the broadband user. So the question is, how do we measure the capacity of a spectrum? How do we measure the capability of a spectrum to support these users with heterogeneous requirements? And this may lead to new modes of spectrum allocation. For example, we can have ephemeral spectrum allocation to offer certain service guarantees. If, for example, we have a critical service running in certain area within a given time, then we can, on an ad hoc basis, allocate spectrum to satisfy critical requirements. For example, this can be for a certain emergency scenario or for certain industrial deployment and so on. And in this sense, we also need appropriate accounting. So we cannot have static databases where we account for how the spectrum is used, but we need a certain form of more dynamic transactions about the usage of spectrum, the levels of allowed radiation, and so on. if we look in general the spectrum usage, we can say that the spectrum regulation is setting the wireless axioms under which we design wireless systems. Then these wireless systems bring new models of communication. In the case of 5G, for example, they brought new trade-offs which arise from heterogeneity. And then we are closing the cycle by requesting new allocations which are going to satisfy these heterogeneous requirements. Let's look into the second point into the further research, which is the question of data-driven performance guarantees. So ultra reliability is one of the new things which came with 5G, and the guarantees of high reliability is certainly one of the most interesting features that 5G wants to offer. But if we look into the fundamental problem in which we have Alice, which is selling ultra reliability to Bob, we have many questions. For example, how does Alice measure the reliability performance? Under what conditions is this ultra reliability guaranteed? How does Alice know exactly the statistical distribution of the signal so that she can guarantee to Bob that his connection will stay alive 99.999% of the time? And in order to tackle this question, we have to go to the anatomy of a connection and look where are the sources of uncertainty. So basically, we have three sources. The first one is the inherent randomness of wireless. The second one is the ignorance about the channel statistics. So we operate in some region where we simply do not know the channel and how the channel behaves. So we have to learn it. And the third one is the change in the channel statistics. So once we learn the channel, the statistics of the channel has changed. There's a concept drift, so we cannot use the same thing that we have learned about that channel to apply later on to predict the performance. So we have taken this into account in a recent research where we have shown that offering high reliability is impossible without data-driven methods and machine learning. So there are three key elements. One is model selection, second is learning, and third one is performance evaluation. And this curve here shows just a conception. This curve shows the concept that in the learning process at the beginning, we have to offer conservative performance, and this performance has started to increase as much as we learn about what is the real statistics of the system. For example, we can choose a very low rate at the beginning when the system is deployed. By the time this rate can start to increase as we learn more about what is the channel statistics and which type of error we can experience. So going to the second topic, that's the requirements from citizens. So when I started to work on the Metis project in 2012, we had a bold vision about 5G offering very high data rate, very dense crowds of users, tactile interactions, remote surgery, connected cars, and so on. But then what is most popular about 5G in 2020 are the protests about 5G. And if you don't believe it, you can check how many times are the videos about anti-5G things shared compared to how much are the videos and articles which are basically explaining what 5G is and what are the possible benefits. So if you go to Amazon and look into the the bestsellers in the mobile and wireless telecommunications, number 12 and actually number 1 a couple of days ago was a book called Death by 5G. This means that we might get new requirements and new constraints into how wireless systems are deployed and operated. So the long-term adjustment and evaluation of radiation levels as it is done now may not be sufficiently reassuring to the general public. So we may need to take a different approach in designing, deploying, and operating wireless systems, where we redefine the procedures for treating the electromagnetic field radiation. So this could, for example, take place when we have a massive rollout of 5G, especially into the millimeter wave frequency region. Then we can have methods and protocols for dynamic control and assessment of radiation. And we also can have methods, monitors, and algorithms for ensuring radiation sustainability of various wireless technologies. And this is partially related to the spectrum allocation and spectrum use issue, which I discussed before. But I think it's an important point here to say that ivory tower attitudes in the wireless engineering community are not sufficient to protect base station towers, which are actually being burned down. Let us now look at the new opportunities for research in beyond 5G and 6G wireless systems. And one that I would like to single out is the true remote presence, which has been an objective for a long time. But the current experience that we have from working online from home tells us that we are still far from it, basically far from immersive experience and interaction with the other participants that are at different locations. So solving this problem in the coming years will require a major interdisciplinary endeavor in communication, signal processing, human-computer interface, artificial intelligence, to name a few. And the need for this is not only due to the current pandemic crisis, but on a long term, this has the potential to decrease the need for travel and basically contribute to the effort to decrease the climate change. Then there are the new communication media and modes. And here I'm primarily thinking about the developments into metamaterials with interesting electromagnetic properties and the quantum elements in terms of computing, communication, and cryptography. So basically, we are in an interesting time where these developments in physics are on their way to become standard elements that could be used as a model of a communication system. In the same way that a transistor is a result of a quantum behavior, of understanding of the quantum effects by physicists, but then by time it became a standard model in a design of electronic systems. So metamaterials, for example, could be basis for creating large intelligent surfaces or reflective intelligent surfaces, and they could play a significant role into guiding, reflecting wireless signals and helping to create better connectivity in certain environment. And of course, it's interesting to look into how the quantum communication elements can be integrated with the classical wireless systems, and what are the modes what are the modes of integration, and what are the benefits that can come from the synergy between these systems. The last one is related to the data markets and smart contracts. Basically, not all IoT devices are or will stay uplink dominated. For example, we have mission critical IoT devices which are already breaking this paradigm by requiring two-way connectivity. So IoT devices will engage, this is my expectation, in autonomous trusted interactions with other devices and humans. So they are going to sell or buy data on the data market, verify trustworthiness of the data, execute certain smart contracts, and so on. So if we look into the legacy system architecture, we look into the IoT devices as being just end devices, providing certain data or receiving certain commands from the infrastructure. But in an architecture which involves distributed trust, there is a much more increased interaction between the devices. So the IoT devices will be more active participants in the network. In terms of communication, this means that this is changing fundamentally the traffic pattern of IoT. So for example, if we use blockchains or other distributed ledgers, they require intensive two-way communication. So the IoT device cannot be just assessed in terms of what is its capability for long battery lifetime and provision of uplink data. So in this direction, we have already shown experimentally that this is happening when we try to integrate IoT with certain distributed ledgers. And for example, this is a setup showing how could we use IoT with integrated blockchain for trusted CO2 emission monitoring, and maybe in the future, trading of carbon emission by smart contracts between IoT devices. So as a final words, I provided biased view on the 5G or 6G communication challenges, and many interesting things which are happening in the research community have been omitted. That's why the view is biased. One important message is that we need to reassess the requirements and methods by following interesting development in related areas, in engineering, but also in physics, health, economics, and so on. And also, I would like to reiterate the fact that it is important to carefully reassess the engineering approaches based on the requirements which are coming from the general public with respect to the deployment and operation of wireless systems.